Hi and welcome to Geeks for Geeks. In this video, we would be discussing the solution of this problem. We are given an array of n integers. So an array would be containing n integers and you would have to find if it is possible to partition the array with following rules. Now, in this problem, suppose the value is 5. So there are 5 elements 8, 3, 9, 1, 2. So by partition, the first thing that comes into our mind is that we would need to partition this array like this. But we don't need to do like this. Rather, you can take it as to group the elements. Why? Because when you would go to the sample test case, you would see that it has not partitioned. Rather, see 8 and 9 is taken into one group, and then 3, 1 and 2 has been taken into another group. So this tells us that we don't need to partition the array, rather we need to group the elements of the array. Now, each element should belong to only one partition. That means that suppose an element can't be a multiple occurrence of that same element into different groups. Each partition should at least have k elements. So a partition should have at least k elements. It boils down to the conclusion that it would have k elements or more than k elements. And the absolute difference. So it means that the maximum element of the partition subtracted with the minimum element of the partition should be less than equal to m itself. Okay. So now let us move to the sample test case. So in the sample test case, they have grouped 8 and 9 into one and 1, 2 and 3 into another. So first thing what you need to do is you need to check if 8 is again present in another. No, 9 is not present, 1 is not present here, 2 is not present here, 3 is not present here. So the first condition is satisfied. Each partition should have at least k elements. So k's value is 2. So yes, this has 2, this has 3. So greater than equal to 2. Yes. Now the absolute difference. So the maximum value is 9 subtracted with the minimum value. The maximum value here is 3 subtracted with the minimum value. So here it is 1 and here it is 2, which is less than equal to 3 itself. Okay, fair enough. So all the conditions are satisfied and we are able to partition the array into two halves. Now there is a thing to notice here. You don't need to minimize or maximize the number of partition. You can partition it in any form. So if we can partition it in any form, then suppose we have 5, 1, 3, 2. So it is very difficult to find the minimum and maximum at each step. So the first thing which you can do is to first sort this 1, 2, 3 and 5. Why? Because the first element would be the minimum and the last element of the partition would be the maximum. And if you have maximum minus minimum, that would give you the absolute difference. But the first thing that you need to find the maximum and the minimum and then find the absolute difference, or use a for loop and be it in one element and search for the other element and for the second element and do it for the second element. What I mean to say is, suppose we have A, B, C, then we would start at the A and we would iterate on B and C. And we would have a variable known as max, which would store the maximum absolute difference. Then we would go to B and we would iterate on C. Okay, fair enough. This is an O(n) square approach. So if we sort it, that would be n log n. And then finding the minimum and maximum would be big O of 1 at each step. And what is n of n? So n log n, let us see if n log n is allowed or not. So we have 2 into 10 to the power 5 multiplied by log 2 of 10 to the power 5. Okay, and that is less than 10 to the power 8. So we can say that yes, this is feasible enough in the time limit. Okay, now let's head back. So we can see that we can't really decide the number of elements at each partition. Why? Because if it was said that all the number of elements in each partition would be equal, then we would have used a binary search approach. First we would have included 1 element, then 2 element, then 3 element, then 4 element, and we could have moved forward and we could have seen what is the feasible one. Okay, suppose this was the question. But this is not a binary search question because the number of elements at each partition differs. So we can't really decide the number of elements at each step. Okay, so number of elements at each partition. So number of elements at each partition can't really be decided because they are very unequal. So now it can be equal, it can be unequal. There is a possibility of unequal, so we can't really go with the greedy approach. Okay, so now whenever we can't decide on something, we should first think about solving it in the form of dynamic programming. Why dynamic programming? Because if we can't really decide on the number of elements, then we need to see every dimension. We need to see every dimension. If we are seeing every dimension, then we should think of recursion or dynamic programming. Okay, this is the thing. Yes, now we know that this is a dynamic programming problem. Now we try to move forward and we need to decide on states. What would be the state of the dynamic programming? So now we know that we need to see every dimension, and this is a dynamic programming problem. This is the proper hint of it. Okay, and what is the intuition? We keep moving forward and we see that we need to see every dimension, and that gives us a sense that this is a dynamic programming problem. Now we head back and we need to decide on states. To decide on states, there is a trick to decide on states for online judge problems. This won't be applicable if the interviewer is asking you, but if you're solving it for online judge problems, there is a possibility. So if it is asked by an interviewer, you can think of the states like O(n) square and n cube. Okay, or you can ask the number of operations or number of elements. But if you go and find the number of elements, it is 2 into 10 to the power 5. Okay, so the deep, and this m is also 10 to the power 9. So if you have something dp states of n cross m, then that would be 10 to the power 14, which is much greater than 10 to the power 8. So a 2D dynamic program, 2D is not possible. So, and the values of the element is also not possible. So if 2D is not possible, then we need to move forward with DP, 1D. So now in 1D DP, the most easiest state you can think of is, first what you should do is, you should prepare a checklist of all the states that is available. If you don't have a checklist of your own, consider asking me on LinkedIn. I would be more than happy to provide it. But now you have a checklist. Now you know that this is a 1D dynamic programming problem. Now, the most simple state you can think of is if possible or not. This is the most simple. If possible till this point or not. This is the most possible. And yes, it is enough to think of this. Think of this point. So what you can do is, you can first sort the array, because we knew that we need to sort the array so that we don't need to have the maximum and the minimum at each step. Then what you can do is, you can have that if it is possible for each I, for each dp of I, if possible, if it is possible to divide it into segments or not. Okay, now we only care about how to implement. Okay, now to implement it, see, we have dp of I. Okay, if it is possible or not. So now in dynamic programming, we should use the pre-computed value to compute the value in the present scenario. Okay, we should have that, because there is a common saying, na, those who don't learn from past are condemned to repeat it. This is a line of dynamic programming. So we should use pre-computed value to get the value at the present person. So now, suppose for dp of I, we should first find the element which is situated just before. Like I'm telling you, suppose we have 1, 2, 3, 8, 9. Okay, so we have 1, 2, 3, 8 and 9. So if we stand at this particular position, then the absolute difference shouldn't be less than 2. See, 3. So now if we go and find 3, 8 minus 3, so we have 5. So the minimum element of the segment where 8 is present should be greater than is equal to 5. Okay, मैं बताता हूँ फिर से. अगर हमें 8 को एक सेगमेंट में इंक्लूड करना है तो वो मैक्सिमम रहेगा बिकॉज वो लास्ट एलिमेंट है. अगर इस 8 को हम लास्ट एलिमेंट बनाते हैं देन उसका फर्स्ट एलिमेंट 5 या 5 से ग्रेटर होना चाहिए. अगर वो 5 से लेस हुआ तो वो मिनिमम एलिमेंट होगा और उसका डिफरेंस ग्रेटर देन के हो जाएगा. ओके, ट्रांसलेटेड द सेम इन हिंदी so that everyone would have a proper understanding. So now if we go and find there is no element, so we need to include 8 in only one segment, and that is feasible because we don't need to minimize or maximize the number of segments. Whatever way we divide, it is more than enough. Fair enough. Now we go to this part and we stand at this position. Then 3 minus 3 is equals to 0. So the first element should be greater than is equals to 0. So if we are searching for an element which is greater than is equals to particular element, then we need to use lower bound. Now what is lower bound? What is lower bound and all? So I would just write LB. So lower bound is a variation of binary search, or you can call it an application of binary search, where if the element is present, then it would report the first occurrence. Report first occurrence. If it is not present, then the next greater element. And we can do binary search, lower bound binary search. Why? Because this is already a sorted array. So this is only facilitates the thing only. So now let us have an example and do a lower bound over there. Suppose we have 1, 2, 3, 4 and 5. Okay, and there is 2. So if we are searching for the value 2, then it would come here and it would report this one. Because if present, it would report the first occurrence. Now suppose the value is 2.5. So 2.5 is not present. So it would report the next value, that is 3. And we want this only. So we would be using lower bound to search an element less than a of I minus k itself. This is what we need to do. Fair enough? So now we know that we need to do this. Now let us move forward. Okay. So we come to the value that is less. So now we know that we need to, so there are two constraints. There is one more constraint here, that at least k elements. So what you can do is you can first find the range, okay, where the first value. So we should first find the range that yes, this elements can be included. Okay. Now we would suppose the range is L. Okay, and we need to just include at least 2 elements, and this is k. So now what we can do is we can iterate from L to k. And we would say that yes, this value is yes. And if at any point, see, for this, suppose we were able to partition till this point. Okay, if we were able to partition till this point, then we can also partition till this point also. Why? Because these all elements are greater than equal to k, and the absolute difference is also followed. We know this. So what we would do is we would first find the range till which we can include the element, and then we would maintain the k bar. Then we would iterate from L to k. First हम क्या कर लेंगे, जो maximum value है हम पहले खोज लेंगे कि कितने elements तक हम include कर सकते, वहां तक चले गए. Okay. अगर and suppose this is greater than equal to k. So I would just help you with an example. Suppose this is the point where we are calculating. This is I, and this difference is k itself. Okay, and this difference is L. Okay, now what is L? Suppose this is a of I, and this is a of I minus k. So all the elements can be included. So now what we would do is we can't go less than k. So we would iterate from this L itself. And suppose at this L position we were able to partition. then we can partition at this point also, this point also, this point also, this point also. This is what we can do. So we would do the same thing at here also. So now we would first use, so what are the proper steps we should do it? First, we need to sort the array. Why sorting the array? Because we don't need to find the minimum and maximum, and binary search can also be applied here. Next, we would stand at I. We would find a of I minus k using lower bound. Using lower bound, because by using lower bound the difference would be less than equal to k, less than equal to m, which respects the condition. Next, we would iterate from L, K, and if at any position we were able to partition till this L point, then we can also partition till this I point also. If this point also is true, we can partition it true. This point true, we can position it to true. But we won't check this position. This point won't be checked. Why? Because if we check this position, then the elements in this would be less than that. Okay. Now let us move to the implementation, and you would have a better understanding of it. So now we are given the value of n, k, m, and a. Okay. Now what we would do is we would define a vector of int with the dp of size n plus 1. Okay. And all the values at 0 itself. That it is not possible. Then we would say that for 0 it is possible. Why we are telling for 0 it is possible? Why? Because the first segment would resolve to this value, okay, before this value. So if this is true, then only this would tell us, yes, this is also true. We would do this. That is why dp of 0 is equals to 1. Okay, fair enough. We would only be operating 0 and 1 because we can directly return that dp of n value. Okay, so now we would simply go and find the return dp of n itself. Okay, fair enough. Now what we would do is we need to sort this value. So a of begin and then a of end to facilitate the min and max and to facilitate the searching of element through lower bound. Okay, this is the reason of this. Now we would move forward and we would start with the first k. Why? Because suppose the element contains two values and it is telling us that at least each segment should have at least 3 elements, but the given element is less. So what we would do is we would start iterating from k itself. So for int I is equals to the value k and I is less than equal to the value n and I. Okay, we have till this point. Now what we would do is we would first find the value of L itself, the point where till which we can take the elements. Okay, now we would have int L is equals to lower bound of what? A of begin. Okay, and then A of n, first the whole array itself. Then what we can do is we need to search this value a of I minus 1 subtracted with the value m, and then we need to subtract a dot by n. Okay, we find the value of L. Now we would have h is equals to I minus k. Why I minus k? Because we need to go till h. From h to I, that element should be included definitely, and that from L to H it would tell us, yes, this element can be included, this element can be included, this element can be included. So it is just telling us this. So we need to iterate from L to H because L is this, H is this, and I is this. So we need to go from L to H. We know that. So for int j is equals to L, and then j is less than equal to H, and j plus plus. Okay, we can do this. Now what we would do is we would say dp of I. If at somehow it is true, okay, dp of I, if that value is true, then this value would also be true. If that value is false, suppose this value is 1 and we need to retain the value. So what you can do is you can write that if dp of 0 is 0, just ignore. If dp of that value is 1, we need to assign that. So this is nothing but the OR value. This is nothing but the OR value because we need to preserve the 1. But if the value comes to if the other value is 1, we need to have that 1. Okay, so what you can do is dp of I is equals to dp of I, or with dp of j itself. And if that value is true, have me true. If that value is false, ignore it. So this is just having that value. Okay, now if somehow we are able to have that particular index we are working as true, yes, the particular index is true, then the work is done and we would break from it. Okay, fair enough. And then we would return dp of n itself. Now let me compile and run this. Okay, this should be lowercase and this should be k. Okay, we are getting a correct output for the sample test case. Now let us submit this and see if we can get an AC or not. And yes, we got an AC. By the way, just to mention, this implementation idea is inspired from Udit Sharma 7. Okay, now that's it for today. Thank you and have a nice day.